Hello, and welcome back to the course on distributed systems and security. This is the first video on the distributed systems part. The purpose of it is simply to kind of align on what do we mean by a distributed system, what is it, why do we consider distributed systems, and what are the kind of the issues that we're interested in when we're programming distributed systems as opposed to a single computer. So there are many systems today that have a distributed nature to them. Even the computer that I'm recording this video on has multiple cores on it. And they communicate with each other by having a shared memory space. That's not the kind of distributed systems we're going to look at in the course. Systems like that are best studied in a course on parallel programming. We will look at distributed systems, which consist of geographically separated machines. They are in different buildings or in different countries, typically in different administrative domains with different system administrators. This means also they do not have a shared memory space. They do not have a shared notion of time. They don't have access to the same notion of time, and therefore can't really use time in a precise manner. They have to do all their coordination by passing messages to each other, typically over the internet. Such systems are also heterogeneous. It consists of very different machines. Some are very strong, always online. Some of them might be very weak, not always online, sometimes out of power. And they will typically be big. The kind of interesting distributed systems out there have thousands or tens of thousands of machines in them. As an example, Dropbox has, as of writing or as of speaking, at least 10,000 machines storing your files, assuming that you use Dropbox. They have millions of clients and they're supporting a wide range of operating systems. Yet, they make it look to you like your file is magically the same and available on all these operating systems. So that's a very nice example of a distributed system solving a task for us. That's the kind of systems we'll be looking at. The way we think about such distributed systems is via a notion called middleware. We have come to kind of realize over, the experience of building such systems, that this middleware notion is the right way to think of systems like this if we want to be able to build them in practice. So what is middleware? It's something that is sitting on top of kind of the usual layer of the ISO-OSI layer, if you remember that one from operating systems. Where the top of it today is basically TCP/IP. Right? So we have the TCP/IP protocol, which allows to send messages between different machines. That's not very rich. There's no semantics to these messages. There's no one keeping track of sessions and where we are in a given protocol. So what we try to do is put a layer in between the TCP/IP layer and then actually the applications we want to build. So you can think of Dropbox like such a thing. So Dropbox is using TCP/IP to make your file available to you no matter where you are, no matter what device you're using. But if you're programming on top of Dropbox, you don't see this. What you're basically seeing is kind of a file system where your files are available. So you can now coordinate between two different machines and different devices by leaving files in your Dropbox folder and writing to them, reading from them. So you have achieved some kind of joint message variable space instead, which is a much more interesting thing to program than message passing. We'll come to learn that later when you do the practical exercises in the course. So that's just an example of a middleware. So to call something a middleware, we have a kind of some concepts we want to throw at it. One of the main things we want available in a middleware abstraction is an API, application programming interface. There should be some kind of standard interface that you use to access the middleware, no matter which kind of device and operating system you're on. We have depicted this like this here. So we think of the middleware layer as being available across different machines. So machine 1 lives here, machine 2 lives here, machine 3 lives here. And the middleware magically kind of appears to be this block that's just present everywhere, like Dropbox is. And then everywhere, I mean, whatever applications we write, they have kind of the same, maybe complicated APIs here they use to access this middleware layer. They can write a file, they can read a file, they can touch a file to update the date, they can log a file, stuff like that. That's an API. Then we would like transparency to the degree that it's possible. Namely, we want this middleware layer to appear to us as if it's not distributed. So for example, in Dropbox, even if my computer is offline for a while, I still have my files, I can still write to them. And there's some kind of magic is under the hood, making sure to update the files when I come online again, unless there was a conflict, in which case the transparency breaks. But up to that point, it really looks like I just have this middleware layer available to me on my machine. So the middleware layer looks like a consistent thing across several platforms. Finally, we would like openness or interoperability, which means that we would like such a system to be specified fully via the APIs. There's nothing going on inside the stomach that we don't know of. And if there is, I mean, it should be written down in a document somewhere so we can all implement it. An example, a very successful example of this is the SMTP email system, which have completely standardized ways of operating, which means I can send an email on my machine and then it will be slowly routed between email servers and then pop up in your inbox at some point. And that means different teams can implement different versions of it on different operating systems, and yet it can all operate together. So that's the middleware abstraction. Now, if we look at something like a middleware, of course, I mean, it itself is running on top of something, in this case, the TCP/IP layer one. And that thing, again, can be broken up into layers, right? So, I mean, middleware layer somehow is just the final layer we see before we start programming it. There's nothing special to it, except probably we have different ways of implementing something like a distributed file system, whereas for TCP/IP, it's pretty standardized. But as we unfold all of these layers, at some point we end up down here on the copper. And magically, you know, we're implementing something like Dropbox by passing signals over copper wires in the ground and Wi-Fi signals in the air. The magic being that these things here, you know, completely hiding away the different operating systems. Of course, the middleware layer is not magic. I mean, it's really a program running here on a single machine. On one operating system, it's one program. On another operating system, a completely different program. That is somehow just magically appearing to us as this magic block here. Okay. So why should you take this course here? So why do we make our life complicated by having distributed systems? I mean, there's a lot of reasons that just come to us so that we do not have a choice. It's not a choice that we have made. Right? One thing is resource sharing. Printers and databases, big telescopes looking at the sky are expensive. We can't all have one. So they are somewhere else than we are. And so if we want to use them, it becomes a distributed system because other people want to use them. So it's a system now consisting of the printer and us and everyone else using the printer. Maybe we also want fault tolerance. Maybe I don't want to run an expensive service on just one machine because it could be down. So I would like to copy my service so it's running on multiple machines and can keep running even if one of them crashes. So I could choose to distribute for fault tolerance. It could also be for scalability, load balancing. So maybe I have a service that's really being used a lot. Like Dropbox, we could in principle implement Dropbox on one good machine. But of course, it has so much traffic, it wouldn't be able to store the files of the world and service them. So Dropbox had to run 10,000 machines instead. So that's another reason that is kind of forced on us if we're successful enough. It can also be efficiency in the sense of economic efficiency. And I'll return to that with an example. It might very well be that the cheapest way to build a system is to build it out of multiple cheap components instead of one very reliable, expensive component. We'll do a very concrete example of that later. Finally, I might want to distribute my system to get autonomy. This is something we see in peer-to-peer systems that we want to run on multiple machines across the globe so no one can take them down. And it's also a prominent topic in cryptocurrency or blockchains, which is up and coming these years, where we want to be able to have a system that cannot be put down by a single person, company, or even country maybe. And if you don't want a server to be attackable by a single person, of course it needs to run on several machines. If it's on a single machine, no matter what you do, someone will have access to the power cable and can pull it. And if all your servers are in the same country, they can be attacked by the laws of that country. So in this case, I mean, if you really want a truly autonomous system, you would have to distribute it across the planet, across several legal systems. Okay, so I hope that settles the why. There's not really a why in it. It's just being put by us, by the environment, that we need to handle distributed systems. And really today, there are no systems left which are not distributed. Then two very prominent concepts in distributed systems are the concepts of replication and consistency. Replication is the distributed part of it. It's the thing that we take something like a file or a service and then we run it in multiple places. I want my file always to be accessible, so I don't put it on one machine, I put it on 3 machines. Or I could even have a service like the Amazon web page, which will cost millions of dollars per minute when it's down. And then instead of running it on one machine, I run it on several machines. So that's replication. I have something that's important to me, so I make many copies of it. That immediately gives you the problem of consistency. Now you have 3 copies of a file. Sometimes one of the servers that store the file is down. Then you write another file. Then that server is down, so you write the other file. And then at some point, the files are not consistent anymore. That's, of course, a problem because you wanted one file. It's just wanted 3 copies of the same file. But the second they start drifting away from each other, you have 3 different files, and then you gain nothing. So that's kind of the flip side of the coin. Consistency, it's not something we do because we want to deal with it. It's something that gets put on us because we replicate. And we like to replicate because it saves us money, it gives us efficiency, availability, and so on. So these are 2 different sides of the coin. And the consistency part is complicated. We'll spend considerable time in the course thinking about how do we keep a replicated system consistent, and what does it even mean? Okay, so that we get back to. Let me try to give one example of this thing with replication for efficiency, where I say it's actually sometimes cheaper to run cheap components, many of them, instead of a single expensive component. Now, this example here is just completely made up numbers, but I hope it gets the point through. Okay, so let's consider the following imaginary story. Let's say I can buy a cheap machine. It costs $1,000, something like the machine I'm recording this on. But now and then it crashes, like the power supply is crappy, or the CPU does weird things, or the disk sometimes crashes. And just to have a number, let's say on any given day, any day, independent of the previous days, it will crash with probability 1 per million. Well, so that means over a year, there's a good chance it's crashing, right? Maybe something like 40%. No, maybe 1/3, 33% approximately. I don't like that. That's a bad number. Like every year, there's a probability 1/3 basically that my system crashes. That's bad. Okay, but I can fortunately buy a more expensive machine. So on the shelf at my hardware pusher, there's this more expensive machine. It costs 10 times as much. However, it is 100 times more reliable. Okay, so it will only crash on any given day by probability 1 divided by 100,000. Right? It costs 10 times more, and it's 100 times more reliable. Surely that's the good deal, right? Turns out it's not. So what I do instead is I buy 3 crappy machines, and then I take a course on distributed systems. That turns out to be the cheap option, because I will teach you how to take 3 cheap machines and then replicate whatever you wanted to run on the expensive machine. Yeah? You run 3 copies of it, each 1 copy on 1 cheap machine, and then build the system such that if you can just ensure that at any point in time, at most one of the cheap machines have crashed, your system will keep running. So it can be machine 1 crashes today, machine 2 tomorrow, and then machine 1, I can boot it up again. And they keep just crashing, but I just hope, I built you a system that will crash only if 2 of them crashes on the same day. Okay? So whenever a machine crashes, I will have a day to maybe buy a new one or replace some component and get it up again, and then another system could crash. Okay? And I can build you that. I'll teach you how to build that. And then if you do the math, and I'll do a separate video on this, also on how to specify such a system and actually give an example with files, how to implement it, you will see the following numbers coming out. Right? So if you take a single expensive machine and you run it for a year, you can see that it will be available every day. It will not crash with probability 99.6%. That's because basically you're taking 365 and dividing by this, but of course you're taking more care because you had probability theory. You end up with this number here, and it will cost you $100,000. However, it turns out that if you can build a system out of 3 components and just tolerate that at most 1 is down at a time, that system will have better availability. It will be available with 99.9% during 1 year, yet it only costs you $3,000. Okay? So cheap, shitty components can be better if you're good at your theory. Okay? So I'm going to teach you how to save money in the course, if nothing else drives you. And as I said, I'll do the simple math of this in a separate video, but try to do it yourself. Another very, very similar and concept is fault tolerance. In distributed systems, we'll talk a lot about fault tolerance. We want to tolerate faults, like 1 out of 3 servers are down. The reason why we need to do that is not just to save money. It's not just to get, replication for fault tolerance. It's because if we don't, we simply will just break with probability 1 asymptotically. So if you take a distributed system like something like Dropbox with 10,000 servers, and then you build your system such that if 1 of them breaks, the entire system breaks, then even a tiny probability of failure will just go up exponentially and make sure that your system is always down. So when you have a big system, you just cannot tolerate that an error in one part spreads to errors in the other parts. That's by definition fault tolerance. Furthermore, when you have a distributed systems, your contact with the world becomes much bigger. If you have something like Dropbox with servers around the planet and hundreds of system administrators, these systems could come under attack, and they are in fact constantly under attack. And therefore, some of the machines might also be taken over by hackers or crashed, and you should be able to tolerate that. So distributed systems are much easier to attack because they have to talk to the network, and the bad guys are out there on the networks, and sometimes also inside your perimeter as drunk system administrators or bad ones. Okay, so that means when you do design distributed systems, you really have to be able to take partial errors, faults, and deal with it. And the general design principle we try to do there is then to design systems such that they kind of tolerate a lot of errors, maybe sometimes by shutting down or becoming slow, but we try to design them such that even under faulty conditions, they are never doing something really bad, like handing out money they shouldn't have given away. And then under fair weather conditions, when they're not being attacked, they're also operating fast and everyone's happy. Yeah? And that's complicated because you have to adapt to the conditions you're in. We'll try to teach you how to do that. So when we're talking about faults, we need some kind of language around what do we want to tolerate, which kind of faults we want to tolerate, and what is even a fault. I mean, some things can be bad for the system, but is really to be expected, and some things could be highly unexpected and also be very, very bad, right? So what is a fault really? Like if a UDP package is dropped, it's really not a fault because that system says packages could get dropped. So you have to live with that. That's hardly kind of a fault. However, if your computer blows up and causes the building you're in to burn down with all your backups, maybe that's a fault. So you should probably be able to, you can then decide whether you want to tolerate that or not, but probably shouldn't have had all your backups in the same building. I mean, this is just kind of some kind of cautious to say it's not always clear what a fault is. With that caveat aside, there is some kind of standard nomenclature in the area, and I'll just go over it here. This is basically just terminology. It's kind of a checklist of failures that you might want to consider when you build your system and think about how do I deal with those. A prominent one is crash failures. So if you have a system with a lot of servers, probably one of them could crash. Okay? So you need to tolerate that. In the literature, we work with various flavors of that. We have what's called fail arbitrary, which means that if a system crashes, a computer crashes, the last thing it will do is send maybe some weird message out. It's probably likely that it could do that. It just crashed, right? That means also the rest of the system should be able to tolerate that some machines might send wrong messages. We'll look at that during the course. There's also what's called fail silent, which means if a computer crashes, it just stops sending. It doesn't tell anyone that it crashed. And then there's this very nice one that's called fail stop, where when a machine crashes, it doesn't send bad stuff out, but it sends like this nice message and say, guys, I'm going to crash now. And then it crashes and it tells the rest of the system. Of course, that's easier to deal with because we now know that it's crashed. This is an example of a theoretical kind of failure type, which still makes sense to consider, and we will consider it because it's something we can kind of implement. We can convert other and worse errors into this kind of thing here, using timeouts and stuff like that. And then there's something called crash recovery, where we want that a machine might crash but then come up again. We have what's called a reset failure, which is this weird kind of failure where we consider processes which might accidentally be reset to an earlier state. Okay? There's again a theory type of failure, but something that we see in the literature. We have timing failures, where maybe a process is slower than it should be. I mean, it should have sent a message before 12 o'clock, but it was completely overloaded, so it couldn't. And now the rest of the system expecting this message will also start to make mistakes. We could also have messages being delayed. I mean, messages travel on the internet, and if we overestimated how fast the internet is, we might have expected messages to arrive before they could. If that happens, we experience a message delay failure. We can have what's called Byzantine process failures, which is something we will actually look quite a lot at in the course, which is failures where we assume that a process in our protocol or in our system has been completely taken over by a bad guy. So think of it as a hacker breaking into the system and now making this process send the worst possible messages. He might even do what's called a monolithic attack, where he's broken into 7 machines across the network and he's able to coordinate them so that these 7 machines will do the worst possible coordinated attack on your system, and still your system should keep running. Okay, so if 7 out of 15 of the machines are being completely malicious, the 8 remaining machines should still operate smoothly and correctly. Duplication errors, these things are about messages. Then it's like you send a message, but it arrives twice. It could easily happen because if the packages are being relayed and resent in TCP/IP and UDP. Injection errors, an adversary sends a message on the networks that should not have been there. Tampering failures, where a message is sent but the adversary changes it. Maybe it's a bad router on the network. Maybe you're using Wi-Fi and it's going through some hacker's computer and it's changing the messages. Messages gets dropped all the time. That's an omission failure. And finally, there can be leakage errors. Oh, that should be a failure there. Where a machine leaks some secret values that it should not have leaked. And that could, for example, be that the machine has some keys for a signature scheme that it uses for signing the messages before sending them. If it accidentally leaks the signing key, that would be really bad, because now some network attacker could start sending other messages in the name of the machine. So such a leakage error could immediately turn into a tampering error or an injection error. Okay. So that's just a checklist. That's the kind of stuff you have to be able to tolerate. Then one of the things we're doing in distributed systems a lot, particularly in this course here, is then trying to mitigate these errors, to make sure that the effect of such an error on the system is not bad. And for some of them, some of the message errors and so on, I mean, some of the mitigation is pretty simple. Like injection errors, we will solve that using cryptography by signing the messages, so an adversary cannot inject messages on our behalf. Some of the crashing things are also easy to mitigate. I'm going to show you that now. And it will leave us almost exclusively with the really hard one, which is the Byzantine errors. And we'll return to that much later in the course. But here's just an example of how to do some kind of very basic mitigation of these failures. So consider the crash recovery failure. So a machine could crash at some point, be offline for an hour while it gets booted, and then come back into the system. How could we deal with that? Well, it turns out we can turn it into this weird reset error where people return to an earlier state simply by doing checkpointing. So we'll just make sure that when we have a distributed system, we don't keep too much in memory. We all the time checkpointing stuff to the disk. And then if suddenly I find myself having crashed and waking up again, I will look at my disk, I'll find the last checkpoint, and then I'll start running from there again. Okay. So we just turned this crash error into a reset error where I might accidentally be put back in an earlier state. We can do even better than that. We can turn reset errors into duplication errors. Remember that a duplication error was this thing that a message might be sent twice. Okay? Doesn't seem too bad, right? We can just use serial numbers and have the receivers route out multiple messages. Right? And we can actually return these take reset errors and turn them into duplication errors only. It's kind of obvious how to do it. So what you do, and this is very inefficient, is whenever you want to send a message, first you checkpoint your entire state to disk. So you just take yourself, put everything on disk. Then you send the message. And then you write on disk, I sent M, and then you start running again. Okay? Of course, you can do efficiency optimizations here, but in theory, I could do this. What do I gain from this? Okay, by the way, if I get reset now or crashed, what I will do is I'll find the latest backup, the latest checkpoint on disk. I'll start running from there again. I know that I did this checkpoint just before sending a message, so when I start running again, this will instruct me to send some message. When I get that instruction, I will check my disk and see if the disk says that I sent M. If I already sent it, I don't send it again. Otherwise, I send it again. Okay? The worst thing that can happen here is that just between, writing the checkpoint down, then I sent the message, and then I crash before I get to write on disk that I did it. So it could be that I get woken up at the checkpoint again, see that I have to send M. The disk doesn't say that I did it, so I send it again. But this is the worst case now. So we turn pretty bad crashing things into just messages might be duplicated. And you know what? They could get duplicated anyway by the UDP system. So this is something we have to deal with anyway. So we just got rid of crashing in principle. Okay. We can then do resending messages until we get acknowledgements back from messages from the receiver and so on. And very, very early arrive at a system where things work pretty well on the crashing machines. And then we start worrying, but now what if someone in the system starts sending wrong messages? Okay. And we'll return to that in great detail later. That was it for the basic setup of distributed systems. What are they? Why are we forced to look at them? And what are kind of the main topics we'll be looking at in the course? So thank you for listening.